In this video, we'll talk about instrumentation amplifiers, derive how they work and why they're better than the difference amplifier that we talked about before. But first, let's review the difference amplifier. This is what it looks like. To operate it, we attach voltage on the input, and on the output, we get a voltage which is equal to an amplification of the voltage on the input. And the specific expression for that is R2 over R1 multiplied by VI1 minus VI2. And now that's under the assumption that R3 is equal to R1 and R4 is equal to R2. Okay, so this is all great, but the problem is the input resistance. The input resistance on these two inputs, on one of them, on input number 1, the input resistance is R1, and on input number 2, the input resistance is equal to R3 plus R4. So two problems. One is that the input resistances are finite, and the second problem is that the input resistances are not equal. Okay, and both of those can cause problems in practical applications. So then we introduce what we call the instrumentation amplifier. And we start off by saying, okay, so the problem that we have is that the two inputs have finite input impedance. Well, we can solve that by just attaching a buffer on each input. So I'm going to draw that here. I'm going to erase this. I'm going to erase this. I'm going to draw a buffer here, okay, like that. Now all I have is just a follower, straight follower on the input. And so now I've solved the problem that the two inputs have finite input resistance and that they're unequal, okay? So it's a large input resistance. Large input resistance, that's supposed to be an N there. So we have large input resistance, so we have solved that problem, okay? So now in principle, we could go home. But one thing that we will learn when we talk about frequency dependence is that it's usually advantageous to distribute the gain approximately equally between the stages. And we will see very shortly why that is the case. And so what we really want to do is we want to maybe have, well, if we have a total gain of N, for example, that we want for our amplifier, then you would want gain of square root N on this stage, and then gain of square root N on these two amplifiers as well, okay? Let's stay on this page. In fact, let's duplicate this page. Which I don't know how to do. Let's not duplicate the page. So if we then add in the resistor stages on this page here, and I'll do that by erasing my doodles like that. With these resistors that are in place now, we'll have approximately equal gain. Okay, the first stage with these resistor values, they'll have a gain of R2 over R1 plus 1, and the second stage will have a gain of R2 over R1, and not such a big deal. But what is a big deal is that usually something like an instrumentation amplifier or a difference amplifier is often intended to measure a small difference in voltages for example, a current sensing resistor on top of a large DC bias. And the problem with this amplifier setup is that if we do it like this, we're going to amplify in each of the two first stages. We're going to amplify in each of the two first stages the bias as well as the small signal that we're interested in. So if I have a gain of 10 on the first stage, for example, for an overall gain of 100, and I have a bias of, let's say 5 volts, the first stage is going to take that 5 volts and amplify it by a factor of 10 to 50 volts. And if my op amps are powered by plus and minus 15 volts, they're not going to be able to produce 50 volts. The design for the instrumentation amplifier solves that simply by removing this ground right here. And that's what we have on the next page. Okay, now we have removed that ground. Everything is still the same. Now let's try and analyze this first stage circuit here. So this first stage circuit here, we understand the second stage is the difference amplifier that we have already dealt with. So the first stage has 2 inputs and it has 2 outputs. So this is an amplifier that has 2 inputs and 2 outputs. Let's start by looking at the current that flows in this direction here. Okay, that's the current I that I've written over on the right-hand side. So that current I, well, at these 2 points here, here's VI1 and here is VI2. So the current is VI1 minus VI2 divided by 2R1, right? The resistor in the middle is 2R1. I can give a new name to that quantity, VI1 minus VI2. I'm going to call that VID, okay? VID. VID stands for input differential, okay? Now, what about the output difference voltage? So I have VO1 here and I VO2 here on the bottom. That difference is going to be equal to that same current I, but that current is going to be flowing in through resistors R1 and R2 on both sides. So that means that VOD, the difference in voltage between those 2 output pins, is going to be equal to this 2 times R1 plus R2 multiplied by that current I, or if I put it all together, it's going to look like this, okay? So the first stage is going to have a gain of the non-inverting gain, a differential gain of the non-inverting gain. So the differences between the 2 inputs are going to be amplified by the non-inverting gain of these 2 amplifiers. Okay, but what about the bias? The bias, which we call the common mode, right? What happens if the 2 inputs are equal? So now I make VI1 equal to VI2. In that case, I have the same voltage here, and my current is equal to 0. That means that the 2 output voltages, the difference in the 2 output voltages is also equal to 0 because there's no current flowing through R2 and R1. And that means that the output voltage is equal to the input voltage. So this is what we call the common mode here, the average of the 2 input voltages. That common mode gets amplified by a unity gain. So what have we accomplished here? We've looked at the difference amplifier, and we've noted that it has finite input resistance and that the input resistors are not equal. Then we tried to buffer the inputs, and that's great. But we like to use them with some gain since we have them there. But when we add the gain, then the bias value of the quantity that we're trying to measure gets amplified as well. However, we can solve that by removing the ground between the two input stages. And the result is that we now have a first stage on the instrumentation amplifier, which has a unity common mode gain. That means that that common bias between the two inputs is not amplified, or it's amplified by a gain of 1. But we have a larger gain on the difference between the two inputs. So the instrumentation amplifier is a superior amplifier because it has high input resistance, nominally infinite input resistance. And it has 2 stages with gain distributed between them, and we'll see why that is advantageous for frequency dependence and bandwidth. And on the input stage, we have a separate common mode and difference mode gain, which is also advantageous because it allows us to measure voltage differences to basically the rail limits of the op amps that are involved.